Hello, my name is Sam and you're watching Wiley Maths. So I promised that I would follow up on my first order differential equations video, and this is the second order differential equations video. So let's get right into it. So we have up here a question: find the general solution to the equation d squared y over dx squared minus 5 dy dx plus 6y equals 0. This is what we would call an ordinary differential equation. That is, since it uses regular differential equations, as opposed to a partial differential equation. It is also homogeneous. It is equal to 0. It is not equal to some other function, as that complicates things, but we will have a look at those examples in just a minute. So this is a very basic version of a second order differential equation, and in order to solve it, we need to create an auxiliary equation. So the way that the auxiliary equation works is we simply replace our derivative with some variable, usually m. So we will say m squared minus 5m plus 6 is equal to 0. Remember, m replaces the derivative, so y as just a function is 0, as that is the integral of m. Sorry, the derivative of m. And then we simply solve for m. So in this example, it's a simple quadratic, two numbers that add to make minus 5 and multiply to make 6. We can see that that will be minus 2 and minus 3. So we have m minus 2 and m minus 3. Therefore, our solutions is m equals 2 and m equals 3. We then must remember the different forms for our general solution. So there are three different types of general solution. This is the first type with real distinct roots, and so we use the form for real distinct root solutions: a e to the 2x plus b e to the 3x. This is our form for two distinct solutions where your roots for m, your auxiliary solutions, are up as your coefficients of x in the powers of e. And that will be our solution to the first question. This is your general solution. So if you wanted to find a particular solution, it would be where you know certain constraints. So if you're trying to model the position of an object related to its speed and its acceleration, if you knew that at y is equal to 0, if you knew at x is equal to 0, say x is time, then the position was equal to 0, and if you knew it started with 0 velocity, then you would be able to find a particular solution telling you anything about the equation. So that's the first question all done. Let's move on to the second one. So now we move on to the second question. Find the general solution to the equation d squared y over dx squared minus 3 dy dx minus 4y equals 8x plus 2. Now, what do we notice is different about this equation? It is a non-homogeneous second order differential equation. Non-homogeneous, standing for that it does not equal 0. It equals some other function of x. So this time we're going to calculate our general solution, what we would call complementary function as usual. That is what we calculated in the previous question. And then we are going to find our particular integral, which just jams on the end. That's the part that is not equal to 0. So we will find our y solution is going to be equal to our y complementary function. That is calculating our auxiliary function and then our general solution. This is our general solution for y. And then we will add our particular integral, this y particular integral. And we'll see how to calculate that in a second, but that comes from the second half of our equation. So as per usual, we will start with our auxiliary equation. M squared minus 3m minus 4 is equal to, now it is not equal to 8x plus 2. It is still equal to just 0. That's because we are only finding the auxiliary equation. We're just looking for those solutions that come with the e part of our final solution. We're not worried about the 8x plus 2 at this point. We're just worried about the differential part of the equation. So we solve this as per usual. Our solutions to this is two numbers that add to make minus 3, multiply to make minus 4. That will be minus 4 and 1. So it factorizes to m minus 4 and m plus 1, and that is equal to 0. So our solutions, m equals 4 and m equals minus 1. So thus our complementary function, again not our final solution, just our complementary function, is equal to ae to the 4x plus be to the minus x. Again, we have two real distinct solutions, so it is of this form. There are other forms for repeat solutions or for complex solutions, but again, that is not this example. So then we need our particular integral. So what do I mean by our particular integral? Well, we need a version of our equation that is equal to 8x plus 2. It is not, this complementary function works for d squared y over dx squared minus 3 dy dx minus 4y is equal to 0. But we want it equal to 8x plus 2. Now 8x plus 2 is a linear function, so we can just add on an extra part to our complementary function to give us our general solution. That's why we add on our particular integral. Now to do this, we find the form of our particular integral, and we get this from the equation. So we start with 8x plus 2. That means our particular integral is of the form ax plus b. If you had, say, just 8x, you would still have ax plus b. You just include the highest order of your variable, and then you add on every lower order on from that, even if it isn't present in the equation. But for example, if you had something like 3x cubed, so if it was equal to 3x cubed, then this means you would have ax cubed plus bx squared plus cx plus d. And that would be the form of your particular integral. That's not the particular integral, it's just the form of your particular integral. So our particular integral is of the form ax plus b. Now what do we actually do with this? Well, we're going to substitute it in. This is a solution almost to our equation, because we want, when is this equation equal to 8x plus 2? So we're figuring out an answer or an example of an answer to our differential equation. So we have our y answer, ax plus b, but we need our dy dx and our d squared y dx squared. So I'm going to write out our ypi, and then I'm going to do a dash up here to signify the first derivative, which is going to be a, as ax differentiates to a, and b differentiates to, well, nothing in terms of x. We then do this again to get our second derivative, which will be 0, as in terms of x, a differentiates to 0. We then substitute this into our original equation. So we're going to have 0 minus 3 dy dx, which is just a, minus 4 of just y, which is ax plus b. And this is going to be equal to 8x plus 2. Lovely job. So now we will simplify the left-hand side and just compare the coefficients to see what our a and b solutions are. So we have minus 3a minus 4ax minus 4b is equal to 8x plus 2. If you're confused about any of this, this is just the expansion of the left-hand side. Don't forget that this minus must also be distributed to your ax and your b. This is not minus 4ax plus 4b, it is minus 4b. So now we compare our coefficients. Well, we have one term here with an x in, and we have one term on this side with an x in. So that's a relatively easy comparison there. So we would have minus 4ax is equal to 8x. We can divide our x. Normally you would not be able to do this, but here we're just comparing coefficients. This gives us minus 4a is equal to 8. Therefore, a is equal to minus 2. We then use the other parts of this equation, the minus 3a, the minus 4b, and the 2. So minus 3a minus 4b is equal to positive 2. We know that a is equal to minus 2, so this is minus 3a times minus 2, which would be 6. So 6 minus 4b is equal to 2, minus 4b is equal to minus 4, b is equal to 1. Lovely. So our particular integral, let's move this down, our particular integral is equal to, that's alright, our particular integral ypi is equal to minus 2x, remember it's ax, so minus 2x, plus b, so plus 1, minus 2x plus 1. Therefore, we can now merge this with our complementary function to give us our general solution. So y general solution, or just y, is ae to the 4x plus be to the minus x, and then we just add on our complementary function minus 2x plus 1, and that will be your final solution for the second question. So this is our third question. Find a particular solution to the equation d squared y over dx squared plus 4 dy dx plus 13y is equal to 26 cos x, when y of 0 is equal to 3 and y dash of 0 is equal to minus 1. So this is a different type of question. It is not asking for a general solution. The previous questions were asking for a solution where if you knew a certain piece of information, you could then specify your solution for that piece of information and thus calculate known answers in a certain scenario. This question is already giving us a scenario. It's saying, well, in this example, at x is equal to, well, at y of 0, our answer is 3, and at y dash of 0, our answer is minus 1. So this is going to be a function y of x. So we're substituting x is equal to 0 in both scenarios. X might be a function for time, in which case this could be measuring the position of some object, but x could be anything, usually time then. So the way that this question works is, again, we're going to calculate our complementary function and our particular integral, as this is a non-homogenous equation. We'll then use this to create our general solution. So you need to find the general solution first. We'll then apply the initial conditions, y of 0 and y dash of 0, in order to calculate the values of a and b. If you remember in the second question, we had ae to the 3x plus be to the minus x. We want to find values for that a and b. So let's start with our auxiliary equation. M squared plus 4m plus 13 is equal to 0. And immediately we can notice that 13 is a prime number. You cannot find two numbers that add to make 4 and multiply to make 13. So you will have to whip out your calculators for this one. And you will probably get complex solutions. So putting this into our calculator, into the quadratic formula, will give you minus 2 plus or minus 3i. So then we can use this complex number to create our complementary function. So we need to recall the form for our complementary function for a complex solution. That is, we have e to the power of our real part of our solution, which is minus 2. Remember that minus 2 is real and 3i is complex, as we have the I component there. So it's e to the minus 2x multiplied by, and then we would have cos, sorry, not just cos, we would have a cos 3x plus b sine 3x. And that will be our complementary function. So we put our complex part of our solution, 3 goes in here and in here. We don't need to worry about the minus because all of these are complex conjugates, so you would have a plus or minus, so they are all of this form with the plus in the middle. And then you have the minus 2 as the coefficient of our x power there. So we need to find our particular integral now. So we can say that ypi, the form of our particular integral. So our function is equal to 26 cos x. So you might think that our particular integral is a cos x. And it's a good idea, but we must remember that this might be some kind of harmonic oscillator. This could be some kind of resonance equation. So we need to add a term for sine as well. So you can get sine in your solution, in your particular integral, and that could then be added on to a complementary function, even if there is no sine present in the original equation. So you must remember that if there is any trigonometric function in your differential equation, then you must have both the cos and the sine in your final in your particular integral. So then we can find the first derivative of our particular integral. So this is going to be Cos differentiates to minus sine, so this will be minus a sine x. Sine differentiates to cos, so this is plus b cos x. I'm sorry that I'm using brackets sometimes here. We then have our second derivative, so I'll add the apostrophe there. We then have our second derivative. Sine differentiates to cos, so minus a cos x. And cos differentiates to minus sine, so minus b sine x. And that will be the three forms of our particular integral. We then have quite the lovely task of substituting all of this into our original equation to find our solutions for a and b. So substituting that in, we get minus a cos x minus b sine x plus 4 of minus a sine x plus b cos x plus 13 of a cos x. I'll just move over a bit here. Plus b sine x is equal to 26 cos x. So these are quite long. This will usually be a function that is a little bit long, so this might take up a lot of the room on your page, but it is necessary. So now we can know our comparing coefficients, and we can do this in a relatively smart way. So obviously we do not care about the coefficients of sine. There is no sine element here, so all of the coefficients of sine are going to add to 0, and all of our coefficients of cos are going to add to 26. So we can create a simultaneous equation for our functions of cos and for our functions of sine. So every coefficient of cos, starting on the left-hand side, we have minus a. We then have we then have plus 4b, because this b is going to multiply with this 4, so we get plus 4b, and plus 13a. And that is going to be equal to 26. Because that is the coefficient of cos x. We can do this again with sine, or actually I will simplify this first to be 4b plus 12a is equal to 26. We then do this with our coefficients of sine, starting with minus b sine x, minus 4a sine x, plus 13b sine x, and that is equal to 0. Again, we can simplify this to be minus 4a plus 12b is equal to 0. This allows us to give us a relation between a and b. So 12b is equal to 4a, and 3b is equal to a. That is dividing this equation by 4. Knowing that 3b is equal to a, we can substitute that into this equation. So 4b is equal to 12, and then each a is equal to 3b. Oh, that's not equal to, sorry, that's plus 12. Substituted our 3b is equal to 26. So 4b plus 36b is equal to 26. Gives us 40b is equal to 26, which will give us a fractional result of 13 over 24b. Thus, a is equal to 3 times b. So a is equal to 39 over 20. So not very nice solutions, but again, you may get fractional answers, and that is just something that you will have to deal with. So our particular integral is thus of the form y particular integral is equal to 39 over 20 cos x plus 13 over 20 sine x. That is our particular integral. So what is our general solution? Well, we add our general solution to our complementary function. So our y general solution is going to be equal to e to the minus 2x times by a cos 3x plus b sine 3x, add our particular integral, 39 over 20 cos x plus 13 over 20 sine x. That's quite a long general solution, but it is correct. That is the full relation for our first question, for our question which we've just looked at. That is, however, not the final answer to our question. It is just the general solution. We are, after all, looking for a particular solution. And the conditions were that y0 is equal to 3 and y dash of 0 was equal to minus 1, as given to us in the question. So now we are basically looking at a completely different question. We can forget the stuff that we've just done, and we instead have our y function, e to the minus 2x, a equals 2x plus b sine 3x plus 39 over 20 cos x plus 13 over 20 sine x. And we simply need to find the values of a and b for when y0 is equal to 3 and for when y dash of 0 is equal to minus 1. So we can start off then by substituting for our first version of this equation. So it is equal to 3, so we can start with 3 is equal to, and then substitute in 0. E to the minus 2 times 0 is going to be e to the 0, which is 1, so we can completely forget about that argument, and instead have a cos of 0 plus b sine of 0, I'll put brackets in here, plus 39 over 20 cos 0 plus 13 over 20 sine 0. And we can simplify this greatly since we know the standard results for sine and cos of 0. So 3 is equal to cos of 0 is 1, so this is a, plus sine of 0 is 0, so we don't need to write any of the b's here. Again, cos of 0 is 1, so 39 over 20. And sine of 0 is 0, so we can forget about that. And already we have a relation for a, and we haven't even started the second part of our question. So a is equal to 3 minus 39 over 20. So 3 is equal to 60 over 20 minus 39 over 20 is going to be 21 over 20, which is going to be our A solution. And lastly, we need our B solution. So to figure out our B solution, we need to differentiate this function. Now this can be quite difficult. It is quite a long function. However, we can actually substitute in our A value as 21 over 20. But that doesn't really help us loads. Sometimes when you do these questions, you'll find that A or B is equal to 0 straight off the bat. That's hugely helpful since it allows you to completely eliminate one of these terms. But that doesn't always happen. So let's write out our new general solution, which is equal to e to the minus 2x times by 21 over 20 cos 3x plus b sine 3x. And then this is all standard. We've seen this before. Cos of x plus 13 over 20 sine x. Lovely jubbly. And then we simply differentiate this. I say simply. It's not a very easy thing to differentiate, and we need to pull together some of the rules that we know. So y derivative of our general solution is equal to. So we have a term here which is multiplied. This first term has an x in, and the second term, when I say second term, I mean the brackets has an x in, as in we have cos x and we have sin x. So this is going to require using the product rule. So we'll start by differentiating e to the minus 2x to be minus 2 e to the minus 2x times by everything that's in our bracket. Again, we've seen that before. And then we will add on just our e to the minus 2x as normal, multiplied by the differential of our bracket. So cos of 3x, 21 over 20 cos 3x. To differentiate that, we pull the 3 out. Well, we multiply the differential of cos, which is minus sine, by the differential of what's in the brackets, which is 3, and then we multiply that by the coefficient. So cos differential is the minus sine, so we'll need a minus. We'll multiply our coefficient by 3, which makes this 63 over 20 sine of 3x. And then we do the same thing over here, but we don't really need to worry about this coefficient. Sine differentiates to cos, so plus 3b cos x. Nice and simple. And then we will add on the differential of our particular integral. So again, cos differentiates to minus sine. Oops, so that's going to be a minus. Cos differentiates to minus sine, so we have minus 39 over 20 sine x. Sine differentiates to cos, so we have plus 13 over 20 cos of x. Lovely, and that is our differential for y. we now substitute in 0 for x. And this is where a lot of the magic is going to happen. So y dash of 0 is equal to minus 1, which is equal to, and then our substitution. So again, minus 2 times by x is 0, e to the 0 is just 1, times by minus 2 will give us minus 2 times this bracket. So we have 21 over 20. This is going to be cos of 0, which is just 1, so we can leave that as 21 over 20, plus b sine of 0. Again, that's going to completely cancel out, so we have no term there, leaving that term as that. Again, minus 2x is 0, e to the 0 is 1, so we don't need to write that. Start our brackets, sine of 3x becomes sine of 0, so we cancel that term out, plus 3b cos x, cos of 0 is 1, so we are left with a 3b here. Moving on to our particular integral, sine of x is 0, so we don't need to worry about this term, that will cancel. And cos of x is 1, so that means we add 13 over 20. Amazing. And now we have an equation just in terms of b. So right now, fully, we have minus 1 equals minus, we can simplify this by cross multiplying. So this 2 will simplify out over 20 to be over 10. So you have minus 21 over 10 plus 3b plus 13 over 20. So we have 3b is equal to 21 over 10 minus 13 over 20 minus 1. So 3b is equal to 21 over 20 is 21 over 10, is 42 over 20, minus 13 is 32, 29 over 20, minus 1 is going to be 9 over 20. So 3b is equal to 9 over 20, thus b is equal to 3 over 20. And there we have it. We have our a and our b solution. So now we are going to get our incredibly long answer. So y, and this is our particular solution, is e to the minus 2x times by 21 over 20 cos of 3x plus 3 over 20 sine of 3x plus 39 over 20 cos of x. I'll move over the screen a bit, plus 13 over 20 sine of x. So those questions are incredibly long. These are the kind of questions where you get a lot of marks for them. However, they're not very common in the new further maths syllabus, as they are only allowed to give you questions up to 6 marks. So for some parts of this question, you might start with the general solution and then have to calculate the particular solution. Or you might start with the differential equation and have to find the general solution. But they will split up these questions into parts. They can't give you something that is 8 or even 10 marks at a time. They have to give you things that are at most 6 marks at a time. And this is, of course, more than 6 marks of working. As you have the whole general solution and particular integral kerfuffle, followed by the particular solution differentiating and then substitution. But yes, that is second order ordinary differential equations with homogeneous and non-homogeneous examples. There are some other things to consider. You must also consider versions of these equations where the coefficient of your second derivative is not 1. It might be some function of x, at which point you have to divide the entire function by that function of x. You can't solve these questions where there is a coefficient to your d squared y dx squared term. So yeah, thank you very much. Thank you very much for watching, and have a great day.